Welcome everyone, and thank you very much for joining today's event. So meanwhile, we give some other time to the remaining participants to join. Just let me say a couple of words. I'm very glad to see you all joining today. Today is the first online technical seminar that our Women in Aerospace Rome Local Group is organizing for this year. And we are very pleased to have a special guest. So Dr. Gioia Rau, an astrophysicist that works at NASA Goddard Space Flight Center, where she works on exoplanets and stellar astrophysics by using artificial intelligence techniques and most advanced computational models and data from the largest telescope on Earth and in space. So after a brief introduction that I'm going to give today, I will give her the floor. And if you hadn't done it yet, I kindly ask you to switch off your cameras and microphones just for the duration of her presentation. That will be the core part of today's meeting. And after that, we're going to have a dedicated question and answer session. And so feel free to just ask everything that you might be interested in asking. And to do that, I will kindly ask you to write your question in the chat of Zoom. And after that, I will call your name and I will kindly ask you to switch on your microphone and camera and to interact directly with Gioia and ask whatever you want to ask her. Okay, so just a couple of words about today's speaker. Gioia Rau obtained her bachelor degree in physics and her master in physics and astrophysics at La Sapienza, University of Rome. Then at the end of her master, she was awarded the fellowship Borsa di Studio per la Tesi all'Estero for being one of the first students among the whole science faculties. And thanks to this fellowship, she developed her thesis at Caltech, JPL. After that, she was awarded with 3 PhD fellowships in Europe, and she decided to go for her doctoral degree in astrophysics at the University of Vienna, where she was awarded with the prize of the best finishing fellowship. And after that, she was awarded a visiting scientist position at the prestigious European Southern Observatory in Germany, and thanks to several projects that she has developed from scratch, she has been awarded also with several grants in Austria, France, and USA. And in particular, of course, last but not least, she is very committed for the promotion of diversity, equality, inclusion, and accessibility, all these values, by supporting women and other underrepresented minorities in pursuing scientific careers. And at the moment, she is working as researcher associate at the NASA's Goddard Space Center. And she's today here with us in order to explain her research and to share how she's applying artificial intelligence on exoplanets and these kind of topics at the NASA Center. So I think that the best now is to give you directly the floor. And so, Gioia, I will ask you to kindly share your screen.
Do you see my screen okay?
Yes.
Okay, that's great. All right, so good morning. Actually, good afternoon for you. Good morning for me. I am 6 hours before you. So thanks for the introduction, Alice. I'm Dr. Gioia Rau. I'm a research scientist at NASA Goddard Space Flight Center and the director of 4 missions concept in development. And today I would like to bring you in a journey to discover evolved stars and exoplanets. So in the 1700s, the philosopher, chemist, and biologist Antoine Lavoisier said nothing is created, nothing is destroyed, and everything is transformed. And also, this is also valid, of course, in our universe. So what are these cool evolved stars that I study? In particular, I will tell you today about these 2 types of objects red giants on the left and red supergiants on the right in this figure that contribute significantly to the chemical replenishment of the universe. And indeed, one of the main open questions in astrophysics is about the cosmic origin of life. So how did we get here? So while primordial nucleosynthesis in the early universe formed hydrogen, helium, and a small amount of lithium, really most of the atomic elements necessary for life as we know it on Earth are produced by nucleosynthesis in stellar interiors. And so it's especially during these late stages of stellar evolution that these heavier elements form molecules and condense into dust grains, which then these stars, through their winds, expel into the interstellar medium. So this expulsion can be slow, like the wind of evolved red giants and planetary nebulae, or explosive, as for supernovae. And then this material directly affects the formation of new population of stars and really constitute the building blocks of planets and eventually life. So that's why these stars are so important to be studied. In fact, most of the elements that make up the human body were formed indeed inside the stars. So think about the calcium in your bone, the iron in your blood, even the oxygen that you're breathing right now were all produced in the stars. There is no other way that the Earth is able to synthesize these chemical elements. They all came to Earth when the solar system was forming. So if this isn't fascinating, I don't know what is. So it's through the sentence, of this famous physicist of last century, Carl Sagan, that said, "We are all made of stardust." But how is the physics of these stars, cool evolved stars, different from the star that we know the most, which is our own sun? So let me give you the example of the comparison between these two. The sun has a radius of only 700,000 kilometers, about 109 times the radius of our own Earth. And if you think this is great, well, think that instead the radius of these red giant stars can reach up to 100 times the one of the sun. So the central figure that I show you here is not on scale, but the one in the bottom right part is. And so not only the dimensions are different, but also the physics of the two stars is quite different. For example, the convective part in the sun extends from a depth of 200,000 kilometers up to the visible surface of the sun, while in the red giants, it's much more bloated, and it includes more than 35 times more mass than the convection in the sun. So let's see how this convection works. So convection is a really important mechanism in these stars, as it is one of the ways of transporting matter. And so it's basically the way in which thermal energy through this convective motion is brought to the outer layers of these stars, so to the surface of these stars. So these convective stellar motions consist of movement of the plasma inside the stars, which usually form circular convective currents that hit the descending plasma, which after rising releases all the energy to the outside. And then it cools, it condenses, and it precipitates again toward the internal part of the star, and then the mechanism starts again. So it's very similar as when you put your water for boiling pasta, to boil. So in the sun, what happened is that we have these very small granules in this image that is taken from a real composition of images from from a solar telescope in Sweden. And so we were able to form this video. So you see these small granules that are on the surface of the sun. And instead, for these very evolved stars, what happened is that these huge convective cells occupy part of the surface of the star. They are really, really big. And also, those are simulations. As you can see, the time is running very fast in the top right part of the stars. So the stars are very far away. It's very challenging to observe them in such a detail. That's why we have to produce these very complex numerical simulations. All right, so how do we study these stars? Well, the ideal way would be in a panchromatic way. So this word comes from the Greek. So pantachromas, so all colors, which translated to the astronomical word means through all the wavelength of the electromagnetic spectrum. And so this is, of course, very difficult to observe to all the wavelengths. What we can do is to put together as many wavelength range of observation as possible. So I produced this figure to show you how really a multi-wavelength is a powerful way to study the stars, accessing the electromagnetic spectrum through these different windows, so to speak, that different telescopes provide us. So in this way, we can really investigate different parts of the physics of these stars. In particular, here I summarize a selection of the telescopes that I use in my research, including the newest JWST, as you can see in the bottom part. And you see that each telescope really works in a very determined wavelength range. And so one of the most powerful techniques to observe these stars, since they are so far away, is interferometry. In fact, interferometry work is to combine two or more telescopes together. Here I show you an example of a photo of the Very Large Telescope Interferometer, which is in a Paranal Desert in Chile. And so by combining the light obtained from various telescopes together, we can create a virtual telescope that has the resolution of a telescope mirror up to the distance between these baselines. Between these telescopes, that is called baseline. And indeed, one of the most important parameter in interferometry is the baseline, or the distance between the telescope, because the resulting resolving power is really proportional to the distance between the telescope or the baseline. And so to give you a practical example, current interferometers, the most powerful one, for example, the Center for High Angular Resolution Astrophysics in California, can resolve details as small as the angular size of a nickel, as seen from the distance of 10,000 miles, which is more than the distance between Honolulu in Hawaii and Rome. So that's a very high resolution. An example of the use of this technique are these very recent images from a study just published a few months ago, showing a stellar spot on the surface of Epsilon Eridani, detected through interferometry and through these interferometers in California, Gioia Rau. This is the very first interferometric detection of a stellar spot on a sun-like star. And this work is really important to distinguish between what is the stellar activity, as in this case, to, for example, an exoplanet passing in front of the star, as I will show you later. Another example of the use of optical interferometry, I want to show you through this video. This video begins with a wide field view of the Milky Way, including the prominent constellation of the Scorpio, and then continues with a zoom into the Earth of the constellation of the Scorpio, where we will find the red supergiant Antares. So what happens is that the final view shows an image of the surface of this star Antares that has been taken with the European Southern Observatory ESO Very Large Telescope Interferometer. And this is the best image ever of the surface and atmosphere of a star. And so through this studio, we also obtained the first map of the motion of the material on a star other than our own sun. So this technique is very powerful. And another amazing result obtained with very large telescope, and then I'm very excited about, and I'm sure you probably heard about it because last year was pretty much in all the media, is about the great dimming of Betelgeuse. So with our team led by Montage, we were able to show, as you can see in this video, to discover that not only this red supergiant Betelgeuse was fading, but also its apparent shape was changing, as you can see here. And so we discovered that the Betelgeuse great dimming results from a localized cooling of the photosphere, which then triggered dust nucleation in a gas cloud ejected by the star months to years before. On the right, instead, you can see the observations of the infrared light being emitted by the dust around Betelgeuse. So the cloud of dust in red and orange are formed when the star sheds all its material back into space, and the central part, which is masked, you see in black, has this little hole, and this is actually what we were able to see on the left. That is circa 24 milliarc seconds in diameter. And so for now, at the moment, we have only interferometers on the Earth. But unfortunately, or actually fortunately, depending on the point of view, our Earth shields us from a certain wavelength ranges. For example, the ultraviolet or some part of the infrared. So Earth's atmospheres prevent us from observing certain wavelength ranges. And so what we have done at NASA is to send telescopes in space. For example, the Hubble Space Telescope, Spitzer, the most recent JWST launched last December. And so now the next steps that we want to do is to launch also interferometers in space. So I'm in charge of the scientific direction of several mission concept development. So those are concepts of space missions that we are ideating and building, developing at NASA in collaboration with other institutes. And so I do not really have time now to show you the details of everything, but of all these missions, but also because they are in development. But stay tuned, because we are studying the feasibility of very futuristic concepts, including one that is very dear to me, to build an interferometer in the UV and optical on the moon. So stay tuned concerning this. So a big other part of my research is dedicated to the search for exoplanets. So for planets outside our own solar system. So you know that in our solar system, is composed by the sun, and we have the planets that are around it. But what is out there? I mean, since the launch of Kepler in 2009, we were able to discover so many planets, and there are a series of observatories in space that NASA has launched, dedicated to the observations also of exoplanets. So here I show you from the left to the right, Spitzer, TESS, Hubble Space Telescope, JWST, and Kepler. And collectively, they are helping us to our journey to search for planets like ours. So there are several ways to discover exoplanets: the radial velocity, the transit, direct imaging, gravitational microlensing, and astrometry. In particular, I specialize on transits and gravitational microlensing. And today I will tell you a little bit about transits. So how does the transit method work? So, for example, that was launched in 2009 and whose mission now is finished, used this method, but also TESS, that instead was launched later in 2018 and is still working. So through this method, the brightness of the stars is monitored in time, and the dips in brightness are detected as planets when the planet is passing in front of the star. So the amount of this dimming tells us about the size of the exoplanets, and the time it takes to complete an orbit tells us how far the planet is from its own star. So periods are measured very precisely, but size are very dependent on the measurement of the size of the star and also on its errors. So Kepler really allowed the pace of discovery to skyrocket. We recently passed the 5,000, the number of 5,000 confirmed planets. So many planet candidates that need other observations to be confirmed. And Kepler also found a wide diversity of planetary architectures. So here are these multi-planet systems found from the very first years of Kepler data. And the orbits are relative to the solar systems to scale, but the planet's size are not. So here is an example of a planetary system found by Kepler, K186. This is an M star, also known as M dwarf or red dwarfs. Those are stars that are smaller, cooler, and therefore dimmer than stars like our own sun. They range in size from 10 to 50% of the sun's radius, and this is on the larger side. So here's a schematic view of this system compared to our own solar system on the bottom. And we see that the entire system fits into the orbit of Mercury almost. The entire system habitable zone. So the definition of the habitable zone is the distance from a star at which liquid water could exist on the surface of an orbiting planet. And therefore, by definition, is the area where the condition might be right, so neither too hot or too cold, for life as we know it to exist. So as I mentioned, more recently in 2018, another telescope has been launched called TESS, and this telescope is still in operation. TESS is really different from Kepler. It has 4 cameras, CCDs, that looked at a portion of a sky for weeks at a time. And it looked at millions of stars to search for periodic dips in brightness that would indicate indeed a planet passing in front of their host star. This is the same method used by Kepler. However, TESS is very different because it has observed almost, as you can see in this animation, the whole sky. While Kepler observed with its field view less than 1% of the sky and found thousands of new planets. So imagine all the new planets that we are still able to find through TESS. For example, TESS found this trio of planets around GJ 357. This is a red dwarf star at 31 light years away from us. So the system Forces planet with 6 times Earth mass is especially intriguing. This planet orbits the outer part of the star's habitable zone. And if this planet has an atmosphere thick enough to keep its surface warm, then liquid water could exist there. So this is very interesting. TESS also found a planetary quadruple orbiting the star L9859, a red dwarf that is located 35 light years away from us. And by the way, if you don't know what is a light year, is basically a unit in astronomy of distance, because is the time that the light is the distance that the light travels in 1 year. So if we were able to travel at the speed of light, we will take 35 years to go to this planetary system, which is very utopistical. Okay, so this image shows a comparison of this exoplanet system at the top with part of our inner solar system, so Mercury, Venus, and the Earth. And it highlights the similarities between the two. So this system contains 4 confirmed rocky planets. The innermost planet is the smallest found by TESS and is 20% smaller than the Earth, while up to 30% of the mass of the 3rd planet could be water. And the existence of the 4th planet has been confirmed, but we don't know yet its mass and radius. And that's why its possible size is indicated by the dashed line. And there are also clues about a potential 5th planet, also with the dashed line, but it's still unconfirmed. And so if confirmed, it will be located exactly in the habitable zone of the system where liquid water indeed could exist. So stay tuned also for this. All right, but these are just very few of the thousands of discoveries that TESS was able to make. TESS still has really many unexplored data. And in fact, he observed the sky so much and produced such a huge amount of data that analyzing them manually one by one will be very long. It will be just impossible to investigate the vast data trove that this telescope was able to give us. And so what we did was building artificial intelligence model, in particular machine learning algorithms, to explore this vast treasure trove of data in the most efficient way possible. So this approach maximizes the human search effort required. And so we applied the use of this machine learning algorithm to search for planet candidates. And we look with this study for these transiting exoplanets in nearly 67 million of full frame images light curve every 30 minutes. And so the strength of our method is that not only it evaluates whether or not the dips in the light curves can be transit, but also identifies a priori light curves that could contain a transit. So through this convolutional neural network that we have trained to identify planetary transit signals and discard false positive, we were able to find 181 new planet candidates. Early last year, also TESS discovered the first Earth-sized planet orbiting in its star's habitable zone. And this world is called TOI 700D. This is a little larger than the Earth and probably a rocky planet. And so based on TESS and Spitzer data, we were able to model potential weather systems, but the analysis of the planet atmospheres, if it has one, will have really to be done with future space mission to study the details of the atmosphere. So how do we do this? TESS was really our finder, but now to study the atmosphere of this planet and understand its chemical composition, we have to do observations with the James Webb Space Telescope. So GWST will be able not only to identify planets, but also will be able to measure what is contained in the atmosphere of these exoplanets. And it will do this through the technique of spectroscopy. So the measurement of the intensity of light at different wavelengths. And so we will be able to study the molecular content of the atmosphere of these planets. And this will be really essential for the exploration of these planets and to identify if, and I repeat, if they can or were able to host life at a certain point. So to let you understand how powerful is JWST, for example, in comparison to the Hubble Space Telescope, I show you here what we will see. So the spectrum of what we will see if we were to observe this planetary transit there. So again, for planets passing directly in front of the star, well, we'll look for chemical footprints, identifying atmospheric gases such as water vapor, carbon dioxide, and methane that absorb a specific wavelength of light. So this is what we were able to observe with the Hubble Space Telescope, practically only water, because Hubble wavelength were able to observe only at that range. And instead, with GWST, it will be really revolutionary because we were able to cover the entire wavelength range in the infrared. Actually, here I show you until 5 micron, but with the instrument MIDI, we will be able to observe down to 10 microns and beyond. And so we will have carbon dioxide, methane, and many different molecules contained in this atmosphere. And we will also be able to study protoplanetary disks formed from dust, where stars and planets form and reveal the chemical makeup of younger and older disks and how this changed over time. All right, so this brings me toward the end of the scientific part of my presentation. But before concluding, I would like to leave you with some messages So for those of you not practical about this, I might be wondering, what does an astrophysicist do? So I got asked this several times. So what do I do in my typical day? Well, I carry out a multitude of commitments. There is teaching, communication, like I'm doing right now. I work a lot with data through programming, through comparing my observations with the model. So we must have a very strong physics and astrophysics background, of course. We go to present our work, or we were going actually, now it's done everything virtually, but hopefully soon we will resume to present our work to conferences where we can, compare and confront our results with other scientists. We even have to do accounting, administration. I have now I'm now mentoring several PhD and postdocs. I have my own PhD student and my intern, and so this is a lot of bureaucratic stuff, but also a lot of mentoring. So I follow their work and I really guide them through this. We work with telescopes, so it doesn't mean that I am at the apex of the telescope observing, as the romantic way will do, will picture us. But it's rather, we get the data. We can even travel to the telescope, but it's rather, we are in front of a computer and we see the data observing on our screen. There is a lot of organizational development there. We write proposal. I also get invited a lot of time to review proposal for panel review. So I get to judge the work of my colleagues, to peer review, and also a lot of science communication and writing. We write articles. And so the daily life of a scientist is really full of challenges, especially for women and underrepresented minorities. So the world as the structure today is often drawn to success, to the big news, but really behind every success there is, and I ensure you that there are a multitude of failures. It is precisely the work of a scientist to have an idea, to build an experiment, and then to verify if this experiment works. And 99.9% of the time, it will never work the first time. So you have a failure and you learn from there how to build your experiment better to make it work. So really one of the most appreciated and necessary quality of a scientist is resilience. Of course, together with hard work and determination. There have been several obstacles that have to overcome through my path. And including, unfavorable environments and environments still full of prejudice toward women and a huge gender gap. And so this is why, one of the reasons why I'm really dedicate a huge part of my time also to support women and underrepresented minorities through several working group and advisory board at NASA on diversity, equity, inclusion, and accessibility. NASA has done really a lot in this regard. It's clear now that it's difficult to completely step behind and stop the biases through training alone. And so structural changes are also really needed. So NASA was really the first one to implement this dual anonymous peer review. It means that not only the proposer for whatever project don't know who are the reviewers, but also the reviewers don't know who is proposing. And so the goal was really to create a change in the tenor of the discussion away from people of the proposing program and really focus solely on the science. And this was a huge success, as demonstrated from the first years of Hubble dual anonymous peer review. There was, during the first year, really a switch between female and male PIs. This dual anonymous peer review was then applied to other programs, and now nearly to all NASA programs. And now Europe is following also with ESO and also other observatories. So here I summarize the qualities that have brought me where I am now, and I believe that young people must cultivate. Yeah, I'm basically at the end of my presentation, and this brings me to the end of my talk. So for any questions, please do not hesitate to contact me if I'm not able to reply to all your questions. So thanks, and I look forward to answering your questions.
Thanks a lot, Gioia. I might say that it was very, very interesting also with the parallel to one of the latest missions that we have seen launched. So thanks a lot for the quite exhaustive presentation and also for the final insight. I found it very, very nice. And I also can see that in the meantime, a lot of people started writing down their questions. So I might say that you kind of catched their attention. So we are also 2 minutes in advance. So if you all agree, I might say that we jump to the question and answer session. So I don't know, Federica, if you are connected, if you want to make a question, otherwise I will go. Okay, so just to optimize, Federica is saying everything that says very interesting presentation on the and field study. Which experiences during your academic years or career would you recognize as the most valuable ones to arrive where you are right now?
Yeah, so for sure, I have learned, and I see now, a posteriori, that doing experiences abroad, it really open up the mind. So not only for a huge professional growing, but also and mostly, well, I mean, mostly for both, but also for a huge personal growing. So really experiencing other cultures, other way of doing, having the adaptability and the resilience to really adapt and discover this new way of doing science, but also living. It's really a huge way that they can make people grow and give them strength. It's in tough time that strength is built, and for sure living in another country and making experience there, it's fun, but it also exposes to many tough times that one has to resolve, and so this really builds strength and character. If this replies to your question. Of course, hard work. I did the classical high school, so the first year of the university were really the toughest for me. So I remember really studying really a lot, especially these during the university years were really tough. So a lot of persistence, and that must be fueled by passion, because otherwise it's very difficult to just continue and persist.
Thank you very much. I would jump to the next one, even if I might say that maybe you covered some of these aspects.
Alicia, you were muted.
Am I?
No, now we can hear you.
Okay, sorry. So I will jump to the next one. Entering more in details, which are the main activities characterizing your current job as research scientist at NASA, even if maybe you already covered this aspect during your presentation.
Again, there are lots of activities. I already answered partially this in my presentation. If you, I don't know, Maria, if you have maybe a more specific question on this, yeah.
Okay, maybe we leave Maria the possibility to add a new question. Then after we jump to the next one, I could see that there was a problem in Right. So thanks, Gioia, for sharing your experience and research. Going a bit more on personal level, which advice would you give to your younger self for boosting the career in the space sector?
That's an interesting question. I think an advice I will give to my younger self or to young girls now is to really believe in themselves. Believing in yourself is one of the most powerful way to progress and to really, you know, do better, really. So, and also say yes to as many things as possible when you are young to make as much experience as you can.
Thank you. And I can see that there is another one from the same person. Which aspect of your work do you enjoy the most?
I enjoy a lot of aspects of my work. It's really a passion for me. So I love the mission building. I love to promote, to really foster DIA values at work. I'm really, really passionate about mentoring. So I love to work with my students and my teams through a mission. Team working is really, it's really something that brings excitement to me. I love to work with data. I love to have observations and, to have this eureka moment. But those are all, it's all part of a job, of my job.
I think within the space sector, we are kind of lucky because, especially if we are passionate about our job, then every morning you wake up smiling because you know that you're going to do something that is going to make you happy during the day. So that's very, very important. I can see now a question from Evangelia. I don't know if you want to mute yourself and to make your question.
Hello. Yes, the question was, you mentioned can you hear me? Sorry.
Mm-hmm.
Okay, yes. The question is, you mentioned in your slides some different methods of detecting exoplanets. I'm sorry, but I'm not an astrophysicist, so I only know the transit one that you mentioned. So what are the advantages and the differences, like briefly, with the other ones? And do you combine these methods just to verify some of your observations?
Oh, yes, absolutely. That's a great question. Thanks. Yeah, so to be able, so when one discovers an exoplanet, to be able to confirm it, one needs at least another observations done with that. So this is how you confirm the exoplanets. So yes, the technique can be combined. There are advantages and disadvantages of all of them, depending on the type of problem that you have. For example, gravitational microlensing events are very rare. So there are surveys dedicated to those kind of detections and work basically on, there are these telescopes observing just this. There are other telescopes searching for transits. Once you discover it with the transit method, then you have again to confirm it most of the time with the radial velocity detection. But for example, the gravitational microlensing technique can give you the mass of the star and the mass of the planet. Its own technique has their own, peculiar way to be useful or not.
So let's say, there is like a standard procedure that is being followed in order to characterize, first detect the star and then characterize its, see its mass, see other aspects.
I'm not sure I understood your question. If your question, if there is a standard procedure to do that? No. So what happened is that, so I just summarized what are the ways to detect exoplanets, and then there are lots of telescopes working on several of these techniques. For example, Kepler and TESS are telescopes dedicated just to scan the sky and to see to look at the transit. So to look basically at light curves and to see if there are dips in the light curves. There are surveys that are dedicated only to gravitational microlensing events, when basically those events are very rare. Then there are telescopes that are dedicated to follow-up observations through radial velocities. There are other telescopes like GSFC that instead observe the atmosphere of these planets, and they search for molecules. So there isn't a standard procedure. It depends what your idea is and how one wants to go for that.
Thank you for the great answer.
Sure.
Okay, so I move to someone new, just to give the possibility to everyone to ask questions. So Saba.
Hi, yeah, sure. Sorry, I thought you'd read my question out, but that's fine. I can say it instead. First of all, absolutely truly remarkable presentation. Thank you so much. You've shared so much insight and knowledge into things. I feel like a student again. I've just been sat here making notes, and that's wonderful because I normally am lecturing my students who sit there make notes. So it's nice to be on the other side for once. I just have a very personal question to ask you. Now, from your experiences in your job, we still see quite a gap between women in STEM and women in space. And I'll tell you from my personal experience that I was discouraged from a very young age to even try to pursue a career in space, let alone STEM. So obviously that derailed. And I've only just recently managed to somehow miraculously get into a startup. So from your personal perspective, in your workplace, do you actually see your workplace personally encouraging women to enroll and also to pursue higher roles within the sector? As a lecturer as well, when you speak to your students, how often do you see your students, your female students, fully supported in their passion to pursue the space sector?
Sure, that's an interesting question. Thanks. Well, first, I speak for myself and not for my employers, but thinking about it, each workplace is made by the people that work into that, right? So as a woman in STEM, a woman in space, I always go to my students as an example, to show them that also they can do it. So I believe that the support must come for sure from higher up, but also from the bottom down. So if we manage to build a change in all the people that work for STEM, I believe that this is the most powerful way to really make an impact and make a change. Of course, we have to make changes also from the beginning, so from the education. I still see that there is a lot to do in this, but that's why I'm so passionate, to dedicate a lot of extra time because it's just volunteering time for me to make this presentation, especially to younger generations, and to come to me with questions.
Thanks a lot again, Gioia. I will move then to Paola Colagrande.
Hello. No, I just want to congratulate with Gioia first, because when she talked about his her educational story, I just hear my story, because I also have classical study. I study physics at Rome, in La Sapienza, and then I worked many years in space domain, and now I'm living in Germany because I'm working for one of the international space agencies and working on space missions and so on. So really, it seems like, look at in the mirror. So, and so congratulations, because you are a very successful example of women in space. And I also I was very, very curious about this webinar, because this year is my first year as member of WIA, so I'm very proud. I'm a member, and I also try to bring this all the information I'm able to collect from all the scientists around the world, and talk to also young students. Sometimes I take lessons at the high school and teaching what is the space, what does it mean, a space mission, to very young people. But it's really rewarding. I mean, it's really nice. But I have a very simple question for you about about your studies, your achievements, because I know that it's really okay. I'm not looking to the deep space. I'm more looking at the Earth and trying to observe what the planet we are living on, and try to preserve this planet. I hope for the next generations. But looking at the other planet, as I read, similar to our planet, what maybe one day we could even live on, but now, knowing that it's almost impossible to reach them, to go them, because the technology is not enough, it's not a bit frustrating. So your passion, I think it's huge. It's really big to continue to work on this, but a bit of frustration or not. Maybe I saw too many science fictions, and I'd like to go there tomorrow.
Sometimes the reality is even beyond science fiction. But well, I mean, to reply to your question, not at all. I don't feel this frustration at all, because I think as scientists, as an innovator, we really have to think 10, 20, even 50 years beyond us. And 50 years ago, we didn't actually, 30 years ago, we didn't even know there were other planets outside our own solar system. So who knows what we will know in 30 years? And who knows where the technology will go? Just 5 years ago, we couldn't even land a rocket. And now we are able to do that as human species. So who knows the technology in 20, 30, 50 years? And I think we have to be really projected in the future. And these exoplanets, the closest to us are 30, 50 light years away. It's not that far away. So I think what we have to do now is not to find a second Earth, so to say, but to save what we have, what we know. It's unique now, and I mean, truly unique, because we haven't found anything similar to the Earth. But at the same time, you know, we search for the curiosity of knowledge, for the curiosity of searching for the knowledge itself. So yeah, I hope this answers your question.
Yeah, of course. Thank you.
Thank you very much. We'll just, we have the last 3 minutes, so we'll go back looking for some other questions that we have jumped, given that we're coming from people that already asked a question. So from Federica, may I ask you, what is your favorite scientific discovery in the field of exoplanet science?
Well, there are several. Some of the one that I show you via test, just because it's telescope that I work with, but also now that they come on top of my head, there is a planet found in the habitable zone around our nearest star, Proxima Centauri, which is very thrilling. Or the first ever image of an exoplanet, but this is already years ago. So, and who knows what GWST will bring us. I'm very excited for the alignment of the mirrors to finish, to see what we'll be able to serve.
Okay, thanks a lot. I'm very sorry for not having the chance to ask all the questions, but as Gioia already mentioned, if you have any other, you can just share them with us or to reach Gioia. I want to thank you very much for participating today, in particular Gioia, for sharing your experience and what you are at the moment focusing on at NASA. I think also from the multitude of questions, you kind of really captured our audience, and I'm looking forward then maybe in the future to cooperate again and to work together for some other activities. Who knows? We need to join forces in general, especially within the DEI topic. So thank you very much, everyone, for joining. Keep posted on the Women in Aerospace Rome local media in the next days for, in particular, the next events that we're going to have. And I wish you a very nice evening, and to you, Gioia, good afternoon, and a nice weekend to everyone.
Just a very quick last question. I said that the workshop, the seminar has been recorded. The recording will be put on available to everyone.
Yes,
on the
we will put it on YouTube, and we will notify on to all the to everyone when it's going to be on YouTube.
Okay, perfect. Thank you.
Thank you, everyone.
Thank you, Alice, for the organization, and thanks everybody for the questions.
My pleasure. Have a nice weekend.